T-minus 3, 2, 1.
Atlas engine ignition.
Liftoff of the United Launch Alliance Delta IV Heavy rocket.
At Space Launch Complex 41, Atlas V rocket is fueled and ready to launch the 5th Mobile User Objective System mission for the United States Navy. Good morning and welcome to Cape Canaveral Air Force Station in Florida. I'm Andrea Linhoff. I'm a parts materials and process engineer focusing on additive manufacturing, also known as 3D printing, at the United Launch Alliance. I'm lucky enough to take a break from my day job and join you here in Mission Control at the Atlas Spaceflight Operations Center. The launch team is not working any issues at this time, and we're proceeding towards a 10:30 a.m. Eastern liftoff. The window for today's opportunity will be 44 minutes. A few seconds from now, at T-minus 4 minutes, the launch count will enter a planned 15-minute hold. This planned hold gives the team time to conduct final systems checks and resolve outstanding issues prior to entering the terminal count. Again, at this point, the team is not working any issues. MUOS 5 delivery on orbit is scheduled to take place nearly 3 hours after liftoff. And because of that long duration, we'll conclude our live coverage approximately 25 minutes after launch. Before we sign off, I'll be joined by Commander Pete Sheehy, representing the U.S. Navy's Communications Satellite Program Office. Commander Sheehy and I will discuss rockets, MUOS, and more. Clay Flynn, the 45th Space Wing Weather Officer, recently briefed the launch team on the current status of the weather here at Cape Canaveral. The probability of violating launch constraints is 0%. The ground winds are 6 to 10 knots out of the east, and the temperature is 87 degrees Fahrenheit. So the weather is within the launch commit criteria and looks favorable for this morning's planned T0 of 10:30 a.m. Eastern. Following nearly a 3-hour flight, the Atlas V 551 will deliver the MUOS 5 to geosynchronous transfer orbit. Let's take a look at some of the events we can expect to see during today's flight.
The following profile details the important events of this mission using approximate times.
T-minus 5, 4, 3, 2, well, you have RD-180 ignition and liftoff of the United Launch Alliance Atlas V rocket.
The Atlas RD-180 main engine and 5 solid rocket boosters ignite to lift the vehicle away from the pad. Shortly after liftoff, Atlas begins its initial pitch, yaw, and roll maneuvers to attain the proper ascent profile and minimize aerodynamic loads. The Atlas V reaches Mach 1, the speed of sound, at 36 seconds. At 51 seconds, the vehicle experiences maximum dynamic pressure. The first 2 solid rocket boosters, or SRBs, are jettisoned at 1 minute 46 seconds into the mission, followed a second and a half later by the remaining 3 SRBs. At 3 minutes 22 seconds, the payload fairing is jettisoned. Approaching booster engine cutoff, the Atlas V is burning propellant at the rate of 1,672 pounds per second, traveling at approximately 12,576 miles per hour, and located 84 miles in altitude and 277 miles downrange. Booster engine cutoff occurs 4 minutes, 23 seconds after liftoff. 6 seconds later, the booster stage is jettisoned. The first Centaur main engine start takes place 10 seconds after booster separation. Cutoff of the Centaur main engine occurs just over 12 minutes after launch. The mission now enters an 8-minute post-phase. At just over 20 minutes into the flight, the Centaur main engine is restarted. This burn will last nearly 6 minutes. Following the second Centaur main engine cutoff at just over 26 minutes, the mission enters a nearly 2.5-hour coast phase. The Centaur main engine is restarted for a third and final burn at 2 hours 49 minutes. Following a 58-second burn, the Centaur main engine is shut down. At 2 hours and 53 minutes, Centaur releases the MUOS satellite for the United States Navy.
ULA is using the Atlas V 551 configuration to launch MUOS 5. This is the 63rd Atlas V launch and the 108th ULA mission. Produced in Decatur, Alabama, the Atlas V 551 is the largest and most powerful configuration in the Atlas V fleet. It is comprised of a Common Core booster powered by an RD-180 engine, 5 Aerojet Rocketdyne solid rocket boosters, and a Centaur second stage powered by an Aerojet Rocketdyne RL-10C1 engine. The MUOS 5 satellite is protected during ascent by a 5-meter diameter payload fairing. Events that took place in preparation for today's launch began on June 4th when the MUOS spacecraft was encapsulated inside the payload fairing. On June 13th, the encapsulated payload was transported to the Vertical Integration Facility, or VIF, at Space Launch Complex 41, where it was mated to the Atlas V rocket. The launch countdown begins with moving the rocket from the VIF to the pad at approximately 8 a.m. yesterday. The quarter-mile trip began using 6 components to complete the 20-minute trip. Weighing in at about 2 million pounds, the Mobile Launch Platform, or MLP, supports the rocket and contains air conditioning, electrical, and commodities, while the undercarriages bear the weight of the MLP and the rocket. 2 rail cars lead the move, with the payload van providing communication to the payload, while the ground van houses the ground support for the rocket. At the rear of the convoy, the portable environmental control system provides air conditioning to the payload and to the rocket. Finally, track mobiles provide the power to move the 3.5 million pound convoy. A third track mobile is added to the front of the convoy to move our largest Atlas V configurations, like today's 551 rocket. The Atlas V rocket stands 206 feet tall, or about 21 stories, and weighs about 1.3 million pounds fully fueled. The RD-180 main engines and 5 solid rocket boosters produce approximately 2.5 million pounds of the thrust to lift the rocket off the pad and begin its journey into orbit. The Navy's 5th Mobile User Objective System satellite completes the initial configuration of an advanced network of orbiting satellites and relay ground stations that is revolutionizing secure, tactical UHF communications for mobile military forces. Users with MUOS terminals can seamlessly connect around the globe with simultaneous crystal clear voice, video, and mission data on a high-speed internet protocol-based system. The MUOS team is led by the Navy's Communications Satellite Program Office. Lockheed Martin is the prime contractor and systems integrator. The artwork on the payload fairing of the rocket recognizes completion of the MUOS satellite constellation, along with ropes symbolizing the Navy's role in the program. Today's launch is dedicated in memory of our colleague, mentor, and friend, Michael A. Marionetti. Mickey, as we fondly called him, was a U.S. Navy veteran and an Embry-Riddle Aeronautical Institute graduate. Mickey was a mechanical engineer for more than 30 years, supporting Atlas and Titan launches from both the East and West Coast launch facilities. He was the lead propulsion engineer on the Titan 34D and 4 vehicles, and for the last 11 years, he served as the engineer in charge of processing the Atlas V solid rocket boosters. Mickey was dedicated to the role he played in helping to create the aerospace history. During his career, he took part in 8 interplanetary missions to help us better understand our universe, and numerous launches like today that benefited the warfighter. His loyalty to his family and friend was beyond reproach, and we would all do well to emulate. He will be missed by all that his path crossed. Godspeed, Mickey.
And OSM, verify the FCO, RCO, and OSM hold fire switches are in the proceed position.
Ready to proceed.
As a 5th and final MUOS satellite is launched from Cape Canaveral, the vision that began many years ago has been achieved. This morning's flight is dedicated in loving memory to MUOS teammates we have lost along the way. Dr. Gary Federici, Deputy Assistant Secretary of the Navy for Command, Control, Communications, Computers, Intelligence, and Space. Jim's also known as James Lewis L. Captain United States Navy, retired Program Manager, Communications Satellite Program Office. Pasquale, also known as Pat A. Caputo, Lead Communications Engineer, the Mitter Corporation. Larry D. Powers, Distinguished Fellow in Space Transport Subject Matter Expert, Integrity Applications Incorporated. Lori Ryan, Senior Systems Integration and Test Engineer, General Dynamics. Ven Vo, Program Manager and President, Vector Planning and Services Incorporated. Patrick, also known as Pat R. Woods, Senior Principal Engineer, Integrity Applications Incorporated. Their legacy quite literally has reached the heavens and stands guard over the service members to whom they have dedicated their time and talents to defend. This is Atlas Mission Control at T-minus 4 minutes and holding. We remain in the planned 15-minute built-in hold as preparations for the launch continue. In a few moments, launch conductor Doug Lebo will pull the launch team for the final go to pick up the countdown. 27 engineers and managers will be pulled for system status and readiness to proceed with the launch. This is the final status check before launch for all Atlas vehicle systems, ground systems, the spacecraft, and the U.S. Air Force Eastern Range. The readiness pull includes hydraulics, pad water deluge system, electrical system, pneumatics, propulsion systems, flight control, and propellants. Let's listen in as launch conductor Doug Lebo performs the final pulling of the team.
Status check to proceed with terminal count. Atlas Systems, propulsion.
Go.
Hydraulics.
Go.
Pneumatics.
Go.
LO2.
Go.
Water.
Go.
Centaur Systems, propulsion.
Go.
Pneumatics.
Go.
LO2.
Go.
LH2.
Go.
Has gas.
Go.
Electrical Systems, airborne.
Go.
Ground.
Go.
Facility.
Go.
RFFTS.
Go.
Flight control.
Go.
Instrumentation.
Go.
COM.
Go.
Timer.
Go.
GC cube.
Go.
Umbilicals.
Go.
ECS.
Go.
Redline monitor.
Go.
Quality.
Go.
Op safety manager.
Go.
ULA safety officer.
Go.
Vehicle system engineer.
Go.
Anomaly chief.
AC is go.
Range coordinator.
Clear to proceed.
Launch director.
The launch vehicle is ready to launch.
Mission director.
This is the mission director. You have permission to launch.
Proceeding with the count. T0 is planned for 1430 Zulu. Set count to start at 1426 Zulu.
Roger. T0 is set for 1430 Zulu. Count will start at 1426 Zulu.
Polling is complete and the launch team has been given the go for launch. From T-minus 4 minutes until launch, you will be listening to launch conductor Doug Lebo and his team performing the final steps in the countdown procedure. You will hear the team call out that Atlas LO2 topping has been secured, followed by about a minute later by the call out for transferring the Atlas and Centaur stages from ground facility power to internal battery power. At T-minus 155, the launch team will command the launch sequencer to start, followed shortly by securing the Centaur LH2 and LO2 topping activity. At T-minus 140, the team will command the flight control system to launch enable and arm the flight termination system. In the final minute, the Atlas tanks will be verified at flight pressures, followed by verification of Centaur tank pressures. A final status check of Atlas, Centaur, and MUOS 5 readiness is conducted at T-minus 25 seconds. Seconds before liftoff, the RD-180 engine ignites and performs a health check, followed by the ignition of the 5 solid rocket boosters to lift the vehicle off the pad. After liftoff, you'll hear the voice of Marty Milanowski providing launch vehicle ascent data.
On my mark, the time will be T-minus 4 minutes and counting. 3, 2, 1, mark. T-minus 4 minutes and counting.
3:55.
Down pilots enabled. SES.
The countdown clock is resumed and we are go for launch at 10:30 a.m. Eastern.
L-minus 3 minutes.
Securing LO2 topping.
Atlas tanks to flight pressure.
T-minus 250.
FTS internal.
$159.
Vehicle internal.
$155.
Launch sequencer start.
$150.
Hearing Centaur LH2. During Centaur lock.
$140.
Launch enabled.
T-minus 90 seconds. The launch vehicle, payload, ground systems, and eastern range are go for launch.
120.
Orcas armed.
FCS count started.
Reduce ECS for launch.
Roger. Vent valves locked.
T-minus 1 minute.
Status.
Range green.
$40.
Stable at step 3.
$28.
ECS reduced for launch.
Roger. Status check.
Go Atlas.
Go Centaur. Go MUOS 5.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition and liftoff of the United Launch Alliance Atlas V rocket carrying the 5th Mobile User Objective System satellite for the United States Navy. MUOS significantly enhances communications for U.S. forces on the move.
Roll program is complete. Mach 1. Booster engine signatures look good. And booster has throttled back up. Max at Q. RD-180s performing well for the set MR. All signatures look good. Currently flying at an altitude of 10 miles, downrange distance 6.8 miles, current velocity 2,400 miles per hour. And booster has throttled back, right on schedule. Signatures look good.
You are hearing the voice of Marty Milanowski
SRB
providing
chamber
launch
pressures have
vehicle
plateaued,
ascent
looking
data.
for burnout momentarily. And the SRBs have burned out. Booster will throttle back up momentarily, and we have begun throttling back up. Signatures continue to look good. Looking for SRB jettison. And we have jettisoned all 5 SRBs at this time. Signatures look good. Closed loop steering has been enabled. Minor body rates associated with closed loop control. Current altitude 36 miles, downrange distance 46 miles, current velocity 4,580 miles per hour. Range track looks good. RD-180 continues to perform well. Bus and battery voltages are stable. Tank pressures look good. Coming up on our 2.5 G throttle segment. And the booster has begun throttling to maintain 2.5 Gs for payload fairing separation. Engine performance continues to look good. Maintain our 2.5 G throttle segment. Tank pressures look good. Bus and battery voltages are good as well. And we have indication of payload fairing jettison. And CFLR jettison. We have now throttled back up to 95%. Engine response looks good. And we've begun throttling to maintain our 4.6 G segment in preparation for shutdown. Boost phase cooldown is underway. And boost phase chill down is complete. Coming up on BECO momentarily. And we have BECO. Engine shutdown looks good. We have retros and stage separation. We have LOX and fuel pre-start. GM2 purge firing of the RCS is underway. We have ignition and full thrust on the RL-10. Centaur steering has been enabled. Signatures look good. RL10 chamber pressures, pump discharge, and fuel venturi all within expected parameters. And we've seen some RCS thermal conditioning firings, prepping that system for use during the burn. Signatures look good. Centaur PU has gone to closed loop control as well.
This is Atlas Mission Control at T plus 5 minutes, 32 seconds. Marty Milanowski just confirmed the successful completion of the early phase of today's flight, and all systems continue to operate nominally. The mission is currently in the first of 3 Centaur engine burns. Our next event, Centaur main engine cutoff, will occur in approximately 7 minutes. I'm now joined by Commander Pete Sheehy from the Navy's Communications Satellite Program Office. Commander, thanks for being here with me today.
Thanks, Andrea. Happy to be here.
I'm excited to learn a lot about the MUOS program, so I'm going to start out by asking you a question about the MUOS. What benefits does this system bring to everyone?
So essentially, MUOS brings disadvantaged users on-demand global communications on the move. And then while doing that, we do it with significantly more capacity, the ability to operate at higher data rates, at greater latitudes, and an IP-based connectivity to networks back home. In addition, each of these MUOS satellites also has a legacy payload, and this will help our existing user base transition more gracefully over time.
Oh, so we're replacing old satellites with new satellites.
With a significantly improved capability.
Perfect. So in terms of the entire system then, can you tell me a little bit about what that is? Right now I know we're launching a satellite, but I want to know more about the MUOS system as a whole.
Sure. We're launching MUOS 5, which is the on-orbit spare. MUOS 1 through 4 are currently in their on-orbit locations. But we also have 2 satellite control facilities, 4 ground stations, and a waveform. And that waveform is intended to be ported into both radios in development, as well as some of the 55,000 terminals that are currently fielded that are upgradable to MUOS. And some of those can be upgraded with as little as a software upgrade.
Oh, great. We know that this is a spare, an orbit spare. Why keep a spare on orbit for MUOS 5? And is this any different than MUOS 1 through 4?
No, MUOS 5 is identical to MUOS 1 through 4. And keeping a spare is all part of ensuring that this MUOS capability that we're delivering will be around for the next 10 plus years. The reason why we keep that spare up on orbit device on Earth is that if one of these satellites reaches their end of life or has an issue, we'll be able to ensure that either the coverage or the capacity impact is minimized to the greatest extent possible. Obviously, launches like what we experience today require months and months of preparation, and that's something that we did not want to wait for. So that's why we keep it on orbit.
Right. There's definitely a lot that goes into a launch. You can't just do it in a couple days.
Nope.
So coming up on July 4th here, I think this is a really appropriate launch to have since we're helping the warfighter. What benefits can warfighters expect to experience using this satellite system?
Well, for the primary end user, and that's that warfighter in the field with a radio or terminal, what we typically think of, they're going to notice the voice clarity, first of all. It's amazing. They're not going to be missing words. They're going to get the right message on the first time. And it's so clear, sometimes you can even understand the tone and the context of the speaker. The next thing they're going to probably start to appreciate is the IP-based connectivity to networks back home. And what that'll allow is the ability to do a lot more communication, but without actually using your voice, and give them, using applications or other network means, a much more effective way to communicate. Third thing they're going to like is the flexibility. This is a very robust, flexible system. Once it is provisioned, you have the ability to go reach the network and get access whenever you need. Now that's that user group. We also have our satellite control facility, or the satellite controllers. They're not going to notice a whole lot of difference, except over time they'll have fewer satellites to fly. And then our other group is the network managers and the maintainers. And those, they're really going to notice a difference, and we're already seeing that today. And the system is so different than the previous system that it's providing some challenges. In some cases, we're having to adapt the way that we do business to this new system, and that's a growing pain. But likewise, this is an area where we're continuing to find areas that we're a little bit immature and we have to keep working at. And so over the next year, I'm really excited about some of the improvements in that area that we can make.
Well, that's some big advancements that we're going to see here pretty soon.
It's pretty great.
That's amazing. So we're going to continue our conversation with the commander in just a few moments, but before we do that, let's get back and check in on our flight. It's important to note that while the MUOS satellites have been providing The Atlas Centaur second stage and MUOS 5 satellite are currently located over the Atlantic Ocean east of Antigua. Our next event, the Centaur Main Engine Cutoff, or MECA 1, is scheduled to take place in about 2 minutes. Once again, here's Marty Milanowski.
About 2 minutes remain in this first burn of the Centaur vehicle. All systems continue to look very good. Our all 10 engine performance is nominal for the ZMR. Centaur continues to burn near nominal, it's just slightly ox-rich. RL10 chamber pressures, LAX pump discharge, fuel venturi, all look appropriate for the ZMR. Tank pressures are stable, storage bottle pressures look good. 1 minute to MECO. Range track continues to look good. Centaur's moving down the middle of the corridor. Current altitude 135 miles. Downrange distance 2,195 miles. And we have IIP vanish. Centaur is now orbital. Centaur PU controlling at nominal MR. RL10 performance continues to be very good. Tank pressures, storage bottles, and batteries all look good. And we have MECO. Engine shutdown is good. We have 4S firings.
This is Atlas Mission Control at T plus 12 minutes 40 seconds. We're a few minutes away from restart of the Centaur main engine. Let's go back to Marty Milanowski.
Degree per second roll rate that we will experience during this ghost phase and has now achieved that.
While we wait for our next mission event, restart of the Centaur engine, let's take a closer look at the MUOS system.
MUOS, the Mobile User Objective System, is the U.S. military's answer to secure and reliable tactical communications for the foreseeable future, and it's being delivered by the United States Navy.
Today we operate globally, and a global joint force relies on global communications. We need secure communications for our operations. The MUOS system will provide secure global communications to the joint warfighter on the move.
There are three critical points for the MUOS program. First, it's operational, supporting the warfighter every day. Secondly, it brings enhanced capabilities over the legacy system. And thirdly, it is critical for the tactical warfighter.
MUOS is a global system, and it allows the communicator to make a call from, say, DC to the Middle East, all in one system. That capability is brand new, and with that capability, it brings a lot of opportunity.
Born from the need for stable 24/7 ship-to-shore communication that could be successful regardless of environmental and geographical conditions, the Navy is assigned the responsibility to provide this vast capability known as narrowband satellite communication.
So from a space accomplishment perspective, MUOS 1 was the highlight of our effort at the time.
The nice thing about MUOS is that the ground system and the terminals contain all the switching and routing technology. The satellite remains unchanged over time, and we can allow technology insertion into the ground and the waveform over time to increase capability without having to make any satellite changes.
MUOS will bring a capability to the joint warfighter that we haven't seen yet. It'll bring smartphone-like capabilities with global communication, with voice, video, and data. The leaders of tomorrow that are growing up today with handheld devices, computing power that we only dreamed about in our day, will find ways to implement MUOS and to lead the joint warfighter in ways we can't even think of today.
The MUOS WCDMA is similar to technology embedded in smartphones all over the world. It brings many benefits and improved capabilities over the legacy SATCOM system. It is already being demonstrated in various environments and for many purposes, like worldwide broadcast, extending SATCOM to individual soldiers, and communications above the Arctic.
The legacy payload we have on the MUOS satellites allow us that smooth transition to a newer, better MUOS capability. We are benefiting from that idea as we are providing the legacy channels for current user, and we are exploring all the capability that MUOS has to offer.
Users with MUOS terminals can seamlessly connect beyond line of sight around the globe. MUOS's new smartphone-like capabilities include simultaneous crystal clear voice and video and mission data on a high-speed internet protocol-based system.
The IP-based nature of MUOS allows network access to unclassified and classified networks. This network access for deployed tactical users will allow the exchange of critical situational awareness and targeting information. As a naval pilot, MUOS will really bring that expanded communications chain, will allow us to coordinate with those forward air controllers, those tactical controllers that need air support at a much greater range. So there'll be less time over the target area. We'll be able to get there, provide the support, and leave.
With that smartphone comes the ability to introduce new applications, new ideas that haven't yet been envisioned by the warfighter. It's exciting to think about over the next 10 years how this system is going to actually be used versus how it was envisioned to be used by the original designers.
Our Navy has a long and tremendous history and heritage in space, but so does our Army. And from the beginning, we've partnered with the Army to provide capabilities that our nation needs. That heritage, that legacy, well, we're building on that today with the cooperation between the Army and the Navy in delivering global secure communications on the move. We work very closely with PEO-C3T on delivering MUOS capability. The terminals, the waveform, the software, the ground stations, and of course, the satellites.
More than just satellites, MUOS is a complex DoD orchestra comprised of a 5-satellite constellation, 4 ground stations across the globe, an integrated waveform, the radios, and complex software to manage the network.
The mission of end-to-end integration is to bring together all of the systems that are required to deliver a MUOS capability to the warfighter. The MUOS program office was responsible for building the satellites and the ground systems and the software that programmed them, but other government program offices were responsible for delivering terminals and the teleport to connect MUOS into the global information grid.
MUOS's design allows it to extend UHF communications further north and south on the globe than ever before. This coverage into polar regions of the world is significant, considering wireless and satellite communications have always been a struggle at those latitudes. Warfighters need satellite communications on a variety of terminals: small, large, man-portable, and airborne. The key to this terminal implementation is the MUOS waveform.
The government makes that waveform available to any of our U.S. vendors who's building a product intended for use by the military. They take that waveform, they implement it on their product, and we assist them in providing laboratory facilities where they can complete their integration work. And the end result is more MUOS products that can put the desired capability into the hands of the warfighter that's suitable for their mission environment.
assuring current capability, developing next-generation communication technology, launching the future.
Navy's been a leader in space from the very beginning of our nation's foray into space. In 1957, the Naval Research Lab launched the Vanguard rocket, carrying the first orbiting satellite that the U.S. would put into space. We've been in space since then, and we will be in the future.
And we have ignition and full thrust on the RL-10. Centaur closed loop stern has been enabled. Body rates look very good. Centaur PU has been enabled. Now commanded in oxidizer-rich condition.
As Marty Malinowski just reported, the Centaur main engine has been restarted for the second of 3 Centaur engine burns. This burn will last approximately 6 minutes. The Atlas V continues to travel in a southeasterly direction. Following our next event, or MECO 2, cutoff of the Centaur RL-10 engine, the Atlas V will cross over the African continent where the trajectory will switch to an easterly heading. Separation of the MUOS 5 satellite will occur over the Indian Ocean, south of Indonesia.
RL-10 response looks good. Chamber pressure, LOX pump, and fuel venturi.
Commander Sheehy, it's great to have you back here again.
Thanks.
I have a couple more questions for you, if you don't mind. My first one, now that MUOS 5 is well on its way to being delivered, can you tell me where we're at with radio capabilities being integrated with the MUOS?
Sure, this is one of the areas that we made significant progress in the last year and a half. Right now we have a waveform that's secure, it's stable, it's very mature, and it's ready to be integrated into many of these terminals that are in development or fielded. We've also come and documented that waveform and come up with the procedures to certify it. And while we've done that, we've stood up 2 labs that we can run through certification. So right now, we have 3 different new terminals that are undergoing that certification testing, and we're looking forward to keep that effort up and accelerate the adoption of MUOS going forward.
Oh, what an interesting increase in capability.
It's excellent.
Awesome.
Okay, Andrea, as you know, you've asked me my questions, and our social media friends and followers, we asked them to send us some too.
Yeah, we did have our friends and viewers come and submit Facebook and Twitter questions. So I guess you're going to be asking me some questions?
I am. Are you ready?
How the tables have turned. I think so.
So at USMC 4066 asks, so how much fuel boils off per minute when you are topping off the fuel tanks?
What an interesting question. So our tanks are not insulated, so there will be some boil off when you get the conduction from the heat on the outside of the tank towards the inside, because we use cryogenic, very, very cold fuels in this process. But the boil off is so negligible that we've never even calculated, how much that approximately is. So it's negligible.
Got it. Well, here's one from Scion Edge. Did the fairing have a new type of acoustic protection?
What a very observant viewer. Earlier in the video, we showed some protection when the MUOS was being encapsulated in the payload fairing. And we also had some pictures online, which is where I feel like that question is coming from. But yes, we are using some fabric protection for the acoustic environments for the satellite as it, goes up into the atmosphere. It's a very harsh environment, so we want to protect the MUOS satellite, which I know is important to you.
And from everything I've heard, this is actually protects it better, and it provides a little bit more clearance for the satellite.
Absolutely. Yeah, the clearance for the satellite is something that I learned recently. We can have you help you launch even bigger satellites now.
Someday. So Rajan K wants to know, to what degree do the main engines gimbal to balance the thrust inequality from one side of the rocket from the SRBs?
Wow, we have some very educated viewers out there. Yes, there are 5 SRBs, so the vehicle is a little bit asymmetrical, but to accommodate for that, we use a 1.5 angle of our yaw engine angle. So 1.5 degrees to accommodate for the off-center of gravity and the asymmetrical solid rocket boosters.
All right.
It's a lot of talking.
That is, for a degree and a half. At DSL Synth has a question in response to a recent video about ULA's avionics team. Comment was, awesome video. Any idea of the number of code lines in the flight software? Must be pretty complex stuff too.
So he was watching our avionics video about our electrical engineering team. You can, if you haven't seen it, it's a really good video. It's on YouTube at our ulalaunch.com or our ULA launch page. But it's a really simple answer. We try to keep our systems very simple. It's simple is better. It's easier for us to understand. So only 40,000 lines of code are used.
Interesting. To put that into perspective, our waveform has well over 1 million lines of code.
I know, it's very simple, but the simpler the better for us so we can understand it.
Great.
Very, very interesting. So now the tables are turning again, and I'm going to ask you some more questions from our Facebook followers. David S. is wondering, if MUOS has smartphone-like capabilities, will soldiers be able to Snapchat and tweet from their MUOS phones? It's all about the apps.
Yeah, that's a great question. I'm sure that our radio vendors and some of our app developers over time will develop tools very similar, maybe not the same, that are going to help our soldiers do their job much more effectively.
Oh, great, great. That's very interesting. Very interesting questions from our viewers. Thanks, Commander. This has been a lot of fun. I think we're going to get back to the flight.
Great.
Coming up on MECO 2 momentarily. And we have MECO. Engine shutdown looks good. We have 4S settling on the RCS. Fuel tank is being vented down as expected. Centaur has begun the turn to the PTC attitude and begun to spin up to the 1.5 degree per second roll rate.
Burns have occurred, and the mission is now in an extended coast phase, with all systems continuing to operate as expected. After completing a 2-hour, 23-minute coast period, the Centaur main engine will be started for a short third burn followed by a short coast period. MUOS 5 delivery on orbit is scheduled to occur at 2 hours and 53 minutes. Because of that long duration, we're going to be concluding our coverage here right now. I want to thank you again, Commander, for enlightening us all about the MUOS program. It's been a real pleasure.
It's been my pleasure to be part of this significant event.
I also really want to thank Marty Milanowski for commenting on today's mission. If you want to learn more information about the Atlas V and ULA, please go to our ULA website at ulalaunch.com. You can also join the conversation on both Facebook and Twitter. We're also on Instagram. We'll complete our live coverage with another look at today's liftoff, which occurred at 10:30 a.m. Eastern Daylight Time. I'm Andrea Linhoff, and on behalf of the entire launch team, thank you for joining us today and have a wonderful day. T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition and liftoff of the United Launch Alliance Atlas V rocket carrying the 5th Mobile User Objective System satellite for the United States Navy. MUOS significantly enhances communications for U.S. forces on the move.